So today we are just going to keep working on partial derivatives and doing examples. So the first problem that I'm going to do is to find all the partial derivatives of the function f of xy is equal to x to the fourth plus 6 square root of y minus 10. So like I said last time, the good way to think about partial derivatives is to, again, imagine your surface. So here's your surface in R3. And then if you're trying to do the partial, let's say with respect to x, then you fix your y. So you imagine that you are at some fixed y is some constant. And you end up getting, if y is a constant, some portion of your function. And if we look at this and we draw our x-z coordinate system, so here is x and here is z, then this curve over here, which belongs to some fixed y, ends up, let's say, looking like this. And then we can think about taking normal derivatives of this curve. And that's just what a partial derivative is of x with respect to z with respect to x while fixing your y. So given that intuition, what we need to think about is what happens if my y is some constant and I'm taking my derivative with respect to x. So partial of f with respect to x over here, and we said another notation could be f subscript x of xy is equal to 4x cubed, and then the y disappears because it's a constant, and the 10 disappears because it's also a constant. Well, let's try to take the partial with respect to y then. So the partial of f with respect to y is going to be equal to the partial of f with respect to y at x comma y. And that is going to be, well, now our x disappears and we get 6 over 2 square root of y by taking the derivative of the square root of y. So then we can ask, what is the partial of f with respect to x at some point? Let's say the point 2, -1. Well, that's the same as partial of f with respect to x at 2, -1. Same idea, different notation. And that's going to be, well, whenever we see x here, we just plug in 2. So 4, 2 to the third power. And similarly, the partial of f with respect to y at the point 2, -1 is equal to the partial of f with respect to y at the point 2, -1. And that will be, well, that actually doesn't exist. So we can say does not exist. Because if we plug in a -1 to this y, we don't get an answer. Does that make, yeah?
Yeah, can you go over how to do it where there's like a constant where they're combined, so like.
So can you give me a function? Partial of f. I mean f of xy. 1 second, problem 2. Yep.
Sorry, I'm trying to find the example.
Yeah, no. Anyone have some problem that they want to do, some function?
Oh,
Right.
yeah, so
Yeah.
it was x squared y, the function is equal to x squared y minus 10y z cubed.
10y(z) cubed. So this is a function, give me a second, with respect to x, y, and z. Yeah,
And then plus 43x
43x.
minus 7 tangent of 4y.
So we did this problem
Yeah,
last class.
yeah, I was just confused with like, because you treat one as a constant, you said I was confused.
Okay, minus 7 tan of y,
4y.
4y. Okay, so let's take the partial of f with respect first to x. So this is going to be, well, you're treating this y as a constant. So you get 2xy, right? If y was like 3, that's what you would get. And then this disappears, and then you get plus 43, and then that disappears. So that's what happens if you take the partial with respect to x. If you take the partial here with respect to y, partial of f with respect to y, then what we get is x squared minus 10z cubed. This disappears, and then you get minus 7 secant squared 4y times 4.
Oh, okay, so now I see how it's.
And then what we can try is we can try to take the partial of f, well, first with respect to x and then with respect to y. And so that will be, well, you go to this problem over here, and now you take the partial with respect to y, and you get 2x. And similarly, you can try to take partial of f first with respect to y, and squared, and then with respect to x. And so that means you go here and you take the partial with respect to x, and you get 2x again, and this part disappears. And so these are equal, which we mentioned last class. And if we go back to problem 1, we can do the same thing. Hello? Okay. So we can do the same thing. We can say, what is the partial of f squared, first with respect to x, and then with respect to y. So we're taking the partial over here with respect to y now. And actually, you can rewrite this using this notation, partial f with respect first to x and then y, right? So that is the partial of y of the partial of f with respect to x. Does that make sense? Yeah.
So if dy and dx were flipped around, would that change the way you?
Yeah, so the x1 says you first do the x and then the y. This comes first. And in this notation, you first do the y and then, sorry, you first do the x and then you do the y. Yes.
So for the f x y, so first we do the partial of x, and you treat y as a constant, and then when you get to y, you treat x as a constant.
Yes. And so then if we are taking this derivative, so this will be equal to, well, you go here, what's the partial of this with respect to y? It's 0, so you get 0. Similarly, we can look at star over here and say, okay, what is the partial of f first with respect to y and then with respect to x? Well, now the notation is partial yx. And again, there's only a y here, so that's 0. So these are equal. Okay, any questions about this? Yes.
I'm pretty sure we said this yesterday, but does it matter the order if you have like partial dx and dy? Does it matter if you do x first or y first?
So generally, yes, but for the functions that we're going to be dealing with, if they're continuous and the second derivative is continuous and like exists and maybe some other things, then they are the same. And for all the functions that we will be dealing with, that will be the case, or most of them.
How would you tell which one to do first? Just like whichever one's left most in the denominator.
Yeah, so this one. Okay. So yeah, you do this one first and then that one. In this case, you do the y first and then the x. And if we are using this notation, you do the x first and then the y.
Okay.
Any other questions? Okay, so let's do another problem then. Problem 3. Okay. Okay, so let's say z is equal to 9u over u squared plus 5v. So, and we can call z f. So f of the uv is now equal to our z. So those are our variables, u and v. So we can ask, what is the partial of f with respect to u? So the partial of f with respect to u is going to be, and now you do the quotient rule because you have a u on the bottom and a u on the top, or it just doesn't matter, but you have a u on the bottom. So this is going to be u squared plus 5v times 9 minus 9u times the derivative of the bottom part with respect to u, so 2u, and the v disappears, over u squared plus 5v squared. Does that make sense? Okay, so we can ask, what is the partial of f with respect to u at the point 1, 1? So that you just plug that in. 1 squared plus 5 times 9 minus 9 times 1 times 2 over 6 squared. Okay, just plugging in the 1 and the 1 wherever we see u and v. We can also ask for the same question. What is the partial of f with respect to v? So again, you have a v at the bottom. So this is going to be u squared plus 5v times the derivative on top, which is 0 with respect to v, right? Because again, u is a constant, minus 9u times the derivative at the bottom with respect to v, which is 5, over u squared plus 5v squared. Yes.
There's no v's in the numerator. Why do you use quotient rule?
So even if you, let's say I had f of x is equal to 1 over x, I still have to use the quotient rule.
Can you just write it as u squared plus 5v to the negative first power? Power rule?
Yeah, you can do it that way too. I think they're the same. Even for when you're using this u, you can do the -1 and then do the product rule. Any other questions? Okay. So now again, we can say, okay, what is f of v at the point, let's say 0, 1? So that's going to be 0 minus 0 over some number, 5, which is equal to 0. So the answer will be 0. And using, for example, this fact that at 1, 0, you get 0, you can tell that your graph at the point 1, 0, so here's your x, here's your, here's your v, and here's your u, and here's your z. So however your graph looks, at the point 1 in the u direction, 0 in the u direction, and 1 in the v direction. So at this point, your graph is flat. Not in the u direction. It might be going. It might look like this, but in the v direction, it is flat. Okay, so maybe it looks something like this. That way, when you move a little bit in the v direction, you're not moving at all in the z direction. That is why your derivative is 0. So the same way you can tell whether functions are flat in Calc 1 using the derivative, or whether they're going up, right? If the derivative is positive, your function is going up, and if the derivative is negative, your function is going down. Similarly, in this case, you can tell a lot from the derivatives about what your function is doing. So for example, if instead of looking at the point 1, 1 over here, I looked at f. I looked at f of u at 0, 1. So what is this? It's going to be u is 0. So this over here is going to be 5 times 9. So 5 times 9 minus, and then that part is 0 because u is 0. And then the bottom part is 5 squared. So we can erase this 5 and we can put a 5 in the bottom. So that's the number that you get. And because that this is positive, we know in fact that as you move in your u direction, fixing v, so as you move in this direction now, where your v is some fixed number, then your graph is going up, right? This is the positive direction. So in fact, this is not how it looks. It looks something like this. So it's flat in the v direction. So let's go here. It's flat in the v direction, but then it's moving up in the u direction. So something like that. Does that make sense? Okay, and we will see in general how to find critical points and classify them using partial derivatives the same way we did in Calc 1. But for now, I just want to continue with doing partial derivatives for 10 minutes, and then we're going to take a quiz. So let's do problem 4. Any questions? So another question is g of x, y, z is equal to x sine of y over z squared. So let's try to take this, the partials of this function with respect to x, y, and z. So the partial of g with respect to x is going to be, and now the x is only on top, and the z on the bottom is being treated as a constant. So you get sine of y over z squared. If we take the partial of g with respect to y, then again, the y is only on top, and the z is being treated as a constant. So we get x cosine of y over z squared. And then if we take the partial with respect to z, so the partial of g with respect to z is going to be z squared times the derivative on top with respect to z, which is 0, so 0, minus x sine of y times the derivative of the bottom part with respect to z, which is 2z, over z to the 4th power. And we can erase this part, and we get a negative, and that's the answer. Any questions about this? Yeah.
For the partial derivative with respect to y, would you multiply 5y?
It's like taking the derivative of cosine f of x is equal to, I mean, you can think about it as taking the derivative of y with respect to y, which is 1, and you get a 1 out here. So that's legitimate. Or you can think about it in terms of f of x is equal to cosine of x, and the derivative of this is just sine of x. Any other questions? Yeah?
It's like, so when you're taking it in respect to z, what is x, y, constants and
Sorry. So here you have this part that is just remains the same times the derivative of this part with respect to z. So that's 2z. And then at the bottom, you just take this thing and you square it. So that's z to the 4. But you can cancel out these, you know, and stuff like that. You can simplify this.
Wait, what happened to this, the 0, like, why is it 0?
For the first part, because the first part is this times the derivative of this with respect to z, and there aren't any z's there, so it's 0. Any other questions? Okay, so let's do another problem. So the next problem is going to be z, problem 5. Z is equal to the square root of x squared plus ln of 5x minus 3y squared. Okay. So let's take the partial of z with respect to x. So this is going to be, at least we're checking all the batteries. Okay. So this is going to be, so let's change the square root to just 1/2. So it's going to be 1/2, the inside part of 5x minus 3y squared to the negative 1/2. So this comes to the bottom, and then by the chain rule, we take the inside part and that derivative with respect to x. So this is going to be 2x plus, and then the ln goes down. So 1 over 5x minus 3y squared. And then over here, we take the derivative of the inside part over here with respect to x. So that is going to be 5. And then we close this. And then we took that derivative. So then we close this. And any other thing? No, and then we're done. Questions?
How do you, what's that last 5 for?
That last 5, so we took the derivative of this ln, right? And that goes 1 over the part inside. And then by the chain rule, we take the derivative of the inside part with respect to x, and that gives us 5, and that gets plugged here. This whole thing is multiplying this part because it comes from the chain rule of the purple part. So this is the purple part chain rule, and then the red part is the red part chain rule.
You said the chain rule and that because it's inside the center log.
Yeah. Any questions? Okay, so let's do the derivative of this with respect to y. So partial of z with respect to y is going to be, well, the first part is the same. We get 1/2 x squared plus ln of 5x minus 3y squared to the negative 1/2. And then the next part, which is the chain rule of this inside part, is going to be the x disappears. So 1 over 5x minus 3y squared. And then we need to take the chain rule of this part, and that's going to be negative 6y. Any questions? Yep. No, sorry. Okay, so if there aren't any questions, we can go to the quiz. Yeah, so please.
Chain rule of it, it's just like taking the derivative of the inside of the natural log.
Yeah, that's chain rule. Right, 1 over this, and then you take the inside, the derivative of this part, and you attach it here with respect to y. So the 2 comes down, and you get negative 6y. And that goes there. All right, it's right over here. Okay, guys, everyone, please be quiet and. Guys, please be quiet, and this is the quiz. When you're done, just hand me a piece of paper and you can go.
It's all like paper.
Yeah, I borrowed.
X times L. Someone have a pen I can borrow?
It's the same, except for this one, right?
Yep. Oh, I mean, you office hours
Yeah.
or after class today?
Other after class.
Yeah. Yep. Same thing, office.
What, so this, what time for what?
Two.
Two. We used to rush when we were there.
First one, I was going to email you last night.
Okay.
I sent it, I submitted it like before midnight, and I submitted it again at like 3 a.m.
It would be graded.
So like, how much of a penalty is it for like,
I'm saying this time it will be graded.
Oh.
Don't worry about it. Okay?
do I have to like leave a message for like a grader or?
No, I'll talk to the grader.
And then I have a question about the test, with the quiz, I guess.
Yeah.
I'm not sure if I did, but if I swap the order for the dy dx and dx dy, that's the only thing I messed up. How much would I lose for that? If I just swap the order
Not
and did
that
the
much.
opposite. Okay. Thank you. Have a nice day.
Did you have a nice week? Okay. The batteries here are, most of them are running out. Are you, sorry, do you know what's on the quiz? Do you still need to see this? Yes. Hanging out, right?
Are you going to see the game?
Am I what?
Going to see the game tomorrow?
No, I don't watch
You don't want, what do you want, soccer?
tennis.
Tennis, oh. Okay. I play tennis. Tennis and soccer. Football, I don't understand.
Do you play around here?
Yeah, just for the game. There's a course in my house. So if my
There's a
neighbor-
court in your house?
My neighbor.
Later. You're where around here?
I stay on Park Forest. Park Forest.
Up there. Oh, court.
Yeah, Park Forest is kind of around the Walmart on top.
Okay.
Are you?
I'm at Forster. They're like 4-minute walk from campus. Yeah, yeah, pretty close. Okay. Yeah.
Is it good? Excuse me, Professor.
Sure. Hi, I'm figuring.